Hello everyone, this is Pengfei from Bytedance Data Platform. Today I'm very happy to have this opportunity to share our usage and the experience of Presto at Bytedance. At Bytedance, we run a cluster of Presto to serve analytics workload for data engineer and scientists. In today's presentation, I will introduce our practice and experience of Presto at Bytedance. This presentation is divided into 4 parts. Firstly, I will give a brief introduction about our OLAP platform and the position of Presto in our platform. And in the second part, I will introduce the work to improve our Presto cluster's stability and maintainability. After that, I will pick some scenarios to introduce how Presto is used in these scenarios and accelerate our data analysis workload. The last part of the presentation is about our ongoing exploration and future plans. So let's move on to the first part. In this part, I will give a brief introduction of our OLAP platform architecture at Bytedance. This slide shows the architecture of our OLAP platform. The bottom layer is storage. MySQL is responsible for the online transactional data storage. Kafka is for event log data storage, and HDFS is for offline large volume data storage. The middle layer is computer engine. We use Spark SQL to handle ETL workload, Flink to handle streaming workload, and Presto to serve ad hoc queries. The top layer is the interface to our users. We provide unified SQL to handle the syntax and the semantics difference between different computer engines. Also, we provide RESTful API and JDBC ODBC connectivity. Besides these three layers, we have 2 auxiliary services. Unified Catalog Service, which is responsible for metadata management of different data sources, and the auth service, which is responsible for authorization and authentication. We started to build our Presto cluster from 2020 and migrate ad hoc workload from Hive and Spark to Presto. And it quickly became popular and grows fast. Now our Presto cluster have tens of thousands compute cores, serve about 1 million queries per day, which cover more than 90% of interactive queries, dramatically reduce the query latency and save a lot of computer resources. This slide gives an overview of our deployment of Presto clusters. We have several independent clusters to serve different user scenarios and deploy coordinators, workers within cluster. In front of these clusters, we deploy a gateway to provide unified user interface. Additionally, we have several auxiliary services. The prediction system is responsible to predict queries execution time based on histogram and runtime statistics. The history server provides a UI for users to view their historical query execution information, and the monitor system collects metrics such as memory usage, CPU usage, and so on, to monitor clusters' operation status and send alert. Given an overview of the deployment of our Presto clusters, in the second part, I will introduce our work in Gateway, Coordinator, and History Server to improve our Presto clusters' stability and maintainability. In our deployment, we have separated our computer resources into different Presto clusters, which are independent with each other. The divisions are mainly based on different usage scenarios. Some of our users run their queries periodically to generate reports. These queries don't require low latency. Some others run ad hoc queries, and query latency is important in this scenario. To provide unified user entry point, we deploy a gateway service in front of Presto clusters. The gateway can route user queries to different clusters based on static rules. However, static rules may cause workload skew between different clusters. When too many queries are running in one Presto cluster, the cluster becomes unstable and the query latency increases. So we implement a dynamic query routing mechanism which will consider cluster metrics such as memory usage, CPU usage, and so on. Coordinator in each Presto cluster will collect the worker's load, calculate the cluster's load, and expose it through RESTful API. The gateway retrieves the cluster load information from each cluster to perform routing and throttling. By combining the static and dynamic routing and throttling strategy, we make a balance between stability and efficiency of different clusters. For one Presto cluster, there is only one coordinator. If it crashes, the cluster will be unavailable. To overcome this issue, we support to deploy multiple coordinators in one Presto cluster. Multiple coordinators register themselves in Zookeeper, and the workers randomly select one coordinator from Zookeeper to report its heartbeat to it. Each coordinator maintains a list of queries processed by itself, and it exposes its query list through a RESTful API so that other coordinators can gather the query list through this API and build a global view of all query lists. Also, each coordinator tracks the memory usage of the queries processed by itself, expose it through a RESTful API, and then gather the memory usage statics from other coordinators. Killing queries that exceed limits is handled by each coordinator, which only kills the query processed by itself. Once a coordinator is crashed, the worker will select a new one to report its heartbeat, and it doesn't affect the cluster's availability. Another factor which makes an impact to our cluster's stability is heavy query, which usually scan too much data and occupy too much compute resources. We provide two ways to avoid this case. The first one is cost-based method. It utilizes the histogram statistics in the catalog to predict the cost of a query and reject queries based on the cost. However, cost-based methods are not always accurate, so we provide the second way to cancel a heavy query as early as possible at runtime. Once a query is running, we keep tracking its runtime statistics, such as input size, finished tasks cost, and so on, and predict how long this query will be executed. If the prediction is above the threshold, the query will be cancelled. By combining these two approaches, we can avoid most of unexpected heavy queries. This slide shows how our history server works. Presto runtime user interface provides rich information to help to analyze query execution. However, it only keeps some latest query execution information and lack a way to view historical query execution information. The history server is designed to overcome this problem. Once a query is completed, the coordinator will dump its execution information into a persistent storage, and the history server can load this information from the persistent storage to provide historical query execution analysis. Additionally, based on the information in the storage, we can easily build a dashboard to extract essential metrics to monitor our cluster's operation status. After introduce our effort on stability improvement, in the third part, I will share 3 main scenarios to utilize Presto at Bytedance. The first scenario is the ad hoc query scenario. Before 2020, we used Spark SQL to solve this scenario. Once a user query arrives, we launch a Spark application and allocate compute resource on Yarn to process it. A lot of time are wasted on waiting the Spark application to start. Besides, due to compute resources can't be shared across Spark application, this approach can't utilize compute resources efficiently. So started from 2020, we began to migrate ad hoc queries to Presto, because Presto is a long-running query service with MPP architecture. This migration dramatically reduced the query latency and saved a lot of computer resources. During the migration, our work mainly focused on how to make Presto be compatible with Spark. In our data warehouse, data engineer and scientists have developed hundreds of UDF using Hive protocol, and they are very familiar with these UDFs. So support Hive UDF is a must-have feature in order to migrate interactive queries to Presto. Hive UDF Wrapper is a feature we developed to let Presto support Hive UDF. This feature extends Presto's function resolver to resolve and load Hive UDF at runtime, and wrapped it as a Presto function to execute. We have created a pull request of this feature in community repo and try to contribute back to community. Besides the Hive UDF, there are a lot of semantic and syntax differences between Presto and Spark. We have done a lot of work to make Presto be compatible with Spark to reduce our customer migration effort. The second scenario is BI analysis. BI platform always provide visualized analysis approach. User doesn't need to write query by themselves. Queries are generated automatically by BI platform using some template. The query patterns are always fixed. This visualized analysis approach usually contains data cube operations such as drill down, roll up, and filter on different dimensions using same dataset. In this scenario, the query latency is important to provide good user experience. High query latency will make the BI platform look like got stuck. So based on above requirements and the characteristics of BI platform, we implemented the materialized view to accelerate this scenario. Our work on materialized view can be divided into 3 parts. The first part is query pattern mining and the materialized view recommendation, which will analyze the historical queries to extract common query patterns based on weighted frequency statistics of table, column, and field conditions. Based on these statistics, materialized view candidates are recommended automatically. The second part is materialized view lifecycle management, which is responsible to invalidate, refresh, and build the materialized view to keep the consistency between raw data and the materialized view. The third part is the rewrite algorithm, which will do query rewrite during query optimization and planning to utilize the materialized view. This slide gave two examples about how the query rewrite works. The example in the left is a join rewrite, which rewrite a query using the materialized view MV1, which contains the same join logic as the query. And finally, add a corresponding field conditions, which is employee ID equals 1 in the final query plan. And the example in the right is an aggregate rewrite, which rewrite a query using the material view MV3. The MV3 is grouped by employee ID and department number, and the query is grouped by the department number. So the final rewriting result is a query plan which grouped by department number based on MV3. From these two examples, we can see the final query plan scan much more less data compared to original query plan. So the execution time will reduce a lot. The final scenario is the near real-time data analysis. This slide contains two chains of data ETL process. The above one is a traditional mechanism. A MySQL bin log and APP event log are collected into Kafka, dumped to HDFS, and then processed by several ETL jobs into Hive tables. Finally, data scientists can analyze the data through query on Presto to retrieve data from Hive table. This approach is called T+1 ETL because the ETL jobs are always heavy and the data lag is about 1 day. To reduce the data lag, we started to investigate on the bottom ETL process using Hoodie. In this approach, we use Spark Flink streaming to consume Kafka data and sync to Hoodie table. Data scientists can analyze the data through querying on Presto to retrieve data from Hoodie table. The data lag can be reduced from 1 day to several minutes. To support the bottom approach, we develop a Hoodie connector to accelerate the query process on Hoodie tables. To support querying Hoodie tables in Presto are implemented in Presto Hive Connect module. The implementation could take advantage of existing code in Presto Hive module, but there are some drawbacks. Due to the MVCC-like design, the file layout of Hoodie tables is quite different from that of regular Hive tables. Mixing the split generation for Hoodie and regular tables make it hard to extend to integrate custom or advanced split scheduling algorithms. By delegating most of our work to Hoodie Parquet real-time input format, memory usage is out of control of the memory management mechanism. That hurts the system robust. Workers tend to crash for OOM when querying a large MOR table. Also, with the evolution of Hoodie project, there will be more new features which are designed specifically for Hoodie. If we continue to cram the code for this kind of feature into Presto Hive module, we will find that it will be more and more difficult to code and test. So we develop a new Hoodie Connect module, which implements the connector SPI as other connectors do. Existing code especially in modules like Presto Hive, Presto Hive Metastore, Presto Parquet, and so on, will be reused. Integrating components from Hive will be quite convenient. The Hoodie connector optimizes MOR table rate by new split generating method to improve split parallelism, and the new page source to enable vectorized Parquet reader, and the push down to improve scan performance. Also, the Hoodie connector makes it more efficient to implement incremental query, insert, update, delete statements on Hoodie table. We have submitted a proposal in community report, and we will contribute back to the community. And the final part of this presentation is about our ongoing exploration and future plans. The first one is our serverless Presto on Bytedance public cloud product. We started this project early this year, and the first version has been released on our company's public cloud, and the second one is investigate on native execution engine techniques to rewrite some operator using C++ to utilize vectorized execution. All these two projects are at very early stage, and we need a lot of effort in the future. That's all. Thank you.
Thank you so much, Pengfei. If you can come back on live, there are a lot of great questions waiting for you. Lot of good innovation that's happening on the UDF side, on the Hoodie front. Of course, we're working on together with Meta, Ahana, Intel, and Bytedance on the native C++ worker as well. Let's take some questions. So first question is, can you share a little bit more details on the materialized view creation, how that's implemented? And is there any automation that is, if you're actually tracking queries and looking at what can be materialized as a part of it, and if you're actually automating that process?
Okay. Actually, the materialized view feature is developed before we start to use Presto. We use it. We developed it using a common optimizer. We use calset to rewrite. Calset is the rewrite algorithm to do the MV rewrite. For the automatically creation and suggestion, we develop a service to collect common query patterns from our historical query information, and this is about a daily workload to mining the common query patterns from the historical queries.
Great, thank you so much. So essentially, you're using the same open source code that Meta open sourced, right? And extending that further internally, is that right?
Yeah.
Materialized views. Got it. All right, let's talk a little bit more about Hoodie. I've seen the proposal that you have to build a new connector for Hoodie to move it out of the Hive connector, right, and have a standalone connector for it. Can you share a little bit about, there's a question about using Hoodie as a part of your ETL. Hoodie is more, more a table format and different from Spark, but maybe you can talk a little bit more about how Hoodie fits into your ETL pipelines, and which engines are you using on top of it, Spark and Presto, or both, or Presto, or both?
From the slide, we can see there are two channels of ETL. The above one is a regular ETL. We use Spark to do the ETL. It's about about 1 day delay. And the bottom one is the streaming approach. We're using Flink streaming and Spark streaming to consume the data from Kafka and insert or update into the Hoodie tables.
Great, thank you so much. And then one last question around caching. So what mechanisms are you using for speeding up query latencies, essentially? What caching techniques are you using? I'm curious, are you using RaptorX already in prod?
We started to use RaptorX or Alexio in recent months, but we have gained too much benefit from them. And we will invest more effort on these two important features in next year.
Got it. So you're still investigating, trying to see what value benefits it can add, and then deploy to production next year.
Yeah.
All right, let's take a look here. Okay. A question about multiple coordinators. So how do multiple coordinators respect the number of queries to run at the resource group level in a cluster? Do you have visibility on what other coordinators in a cluster are running?
Actually, we only registered the coordinators. Actually, we only registered the coordinators in the zookeeper, and we expose the query information. But the coordinator exposes the query information belongs to itself through a RESTful API. So if we want to query all the query list, the coordinator need to send the REST request to other coordinators to retrieve all the query list, the global query list. It can be a view, I think. Yeah.
Got it. Thank you so much. So, are you using the project that? So the question is from Swapnil, who will be presenting later in the day, actually, on multiple coordinators that's deployed at Meta. You are just to confirm, you are using the same capabilities that are already available in open source. Is that right?
Actually, for the multiple coordinators, we developed by ourselves.
Okay. So you might want to listen to the session that Swapnil has later in the afternoon on how multiple coordinators are built into Presto now, and each coordinator can manage the workers on their own, and you might save some complexity of the zookeeper that you have right now.
Sure.
Any other questions, folks, that we haven't answered yet? Last call on questions for Pengfei, coming live all the way from Shanghai. Pengfei, thank you again for joining. It's a really early in the morning or really late at night, whichever one it is. But a great session. I mean, one of the key stats that I will remember for this session is 1 million queries running on Presto a day. And that is obviously incredibly impressive, given that you just started using and running Presto a year ago, a little over a year ago. And so great to see how mission critical Presto has become in such a short period of time, and is pretty much being used as the de facto data warehouse and analytical engine across Bytedance. All right, I don't see any other questions coming in. Great session, Pengfei. Thanks again. We'll talk soon. And I think you have a meetup coming tomorrow in Shanghai, at Shanghai time as well this time around. So good luck with that. Thanks, everyone. Let's jump to the next session, which starts in 5 minutes. These are three lightning sessions on three different topics. And now is the time you switch over, leave this room, and go jump into another room. Cheers. Bye.